Okay, good afternoon, everyone. I'm going to talk about improving integration process efficiency through pull request prioritization. The presentation is organized as follows. I will start by describing the context and the motivation of the work. Then I will introduce the problem, and next I will explain the proposal of our work. After explaining the proposal, I will explain how we evaluate it, and then I will show the result obtained in our work. The presentation ends by commenting on the conclusions and future works. I'm going to start by giving a context of the problem and explaining the motivation of this research. In the pool-based development model, project administrators maintain a main development branch, and contributors propose their changes through pull request submissions. Contributors make their changes in a new branch fork from the latest version currently available on the main development branch and make the necessary changes. This branch is usually called a future branch, and then the changes can be committed on the branch so as to enact them. And when the development is achieved, a pull request is submitted to ask the project administrators to include the changes into the main development branch. Next, project administrators must review the pull request, and as a result of the review process, the pull request can be closed as accepted or rejected. Finally, if the pull request is accepted, then it is merged by a project administrator. So in large project, the number of pull requests, of incoming pull requests is quite a challenge. So prioritizing pull requests is one of the main concerns of project administrators in their daily work. Now I'm going to explain the core of the problem. Since contribution can be submitted concurrently, more than one pull request can be proposed changes that modify the same part of the code. When two pull requests are concurrently open on a given target branch and propose different modification for identical code parts, then a pairwise conflict exists. In that case, only the first one can be integrated automatically, while the second requires conflict resolutions. The pull request integration sequence is the chronological order in which the project administrators integrate the pull requests. The pull request integration sequence defines the integration process. An integration process is more efficient when it keeps the main development branch as up to date as possible while solving fewer conflicts. So the efficiency of the integration process is affected by the number of conflict resolution required and the delay of less conflicting pull request integrations. Let's see two examples to understand how the efficiency of the integration process is affected. The first example, let's see a possible integration process for 3 pull requests. Let's suppose that the changes of pull request 1 conflict with the changes of pull request 3, and the changes of pull request 2 conflict with the changes of pull request 3. So there are two pairwise conflicts, one between pull request 1 and pull request 3, and another between pull request 2 and pull request 3. Pull request 3 is integrated first, and it can be integrated automatically. But the other two pull requests requires a conflict resolution because they conflict with pull request 3, which is already integrated. Now let's consider another integration process for the same pull request. In this case, the pull request 1 and pull request 2 are automatically integrated, and pull request 3 requires a conflict resolution. So the integration, in the second integration process, the number of required conflict resolution is smaller than the first one, and therefore it is more efficient. And the second example, let's consider another example. In this example, the changes of pull request 1 conflict with the changes of pull request 3. Pull request 1 is integrated first and it can be integrated automatically, but pull request 3 requires a conflict resolution because it conflicts with pull request 1, which is already integrated. And lastly, pull request 2 can also be integrated automatically. The problem in this case is that the integration of pull request 2, which does not conflict with any other pull request, was delayed. It will be more efficient to integrate pull request 2 before pull request 3, so that the main development branch is more up to date at not additional cost. Now I'm going to introduce the core of our proposal to the problem seen before. The idea is to consider the integration cost as the number of per web conflict to be solved, and the gain as the number of integrated pull requests. We propose to consider the integration process efficiency as the fact that for a given integration cost, the highest gain, possible gain is reached. Therefore, to achieve an optimized integration process efficiency, the number of conflict resolutions should be minimized and the least conflicting pull requests should be integrated earlier. We propose a process that provides a sequence of unconflicting pull request groups that minimize the number of conflict resolution and defines an optimized integration order according to the efficiency of the integration process. I will first explain the approach and then show an example to understand it better. The approach lies on a 4-step process. The first step is the per web conflict representation. It processes the set of pull requests to obtain the existing per web conflict and generate a per web conflict graph where nodes represent each individual pull request and edges represent the existence of merge conflict between pull request pair. The second step is the unconflicting pull request clustering. It processes the per web conflict graph to generate a set with the fewest possible groups that each contains unconflicting pull requests. Our approach solves this clustering problem as a graph correlation problem. The third step is the unconflicting pull request group representation. It consists in representing a complete graph whose nodes represent each unconflicting pull request group from the previous step and whose edges correspond to integration conflict between pull request groups. And lastly, the fourth step is the pull request group integration sequence optimization. This step provides an ordered set of pull request groups which constitutes our calculated optimized pull request group integration sequence according to the integration process efficiency. This order is calculated by traversing the pull request group graph to search for the best trade-off that maximizes gain while minimizing cost. Let's see an example of each step of the approach. The first step obtains the per web conflicts and builds the related per web conflict graph. Next, the second step applies a coloring algorithm to get the unconflicting pull request groups. Then the third step builds the pull request group graph. And lastly, the fourth step traverses the pull request group graph to get an optimized pull request group integration sequence. The traverse algorithm starts with the heaviest node and then calculate for each node to be visited the trade-off between the gain, that is the number of pull requests to be integrated, and the cost, that is the number of per web conflict to be solved. So the next node to be visited is the node with the best trade-off. Then from the last visiting node, it calculates the other path to the nodes not already visited. In this example, we only have one more. So C2 is the next node to be visited. So that the pull request group integration sequence is C0, C1, and C2. Now I'm going to explain how we evaluate our proposal. We set up a case study that consists in extracting integration sequences from the history of a software project and applying our approach to the set of pull requests for each integration sequence. We select the Until for project since it's publicly available in GitHub. It is popular because it has more than 10,000 forks, 10,000 starts and 2,000 forks, and follows the pull-based development process. Further, its history has more than 1,000 pull requests, which is an adequate number to evaluate our proposal. We extract the iteration sequence from the project history by extracting the integrated pull request within for a 14-day time window. The figure shows all the possibilities according to the pull request project lifecycle for a time window. We obtain an iteration sequence by extracting integrated pull requests within the time window. In the figure correspond to the pull request type 5 and 6. And then sort these pull requests by their integration timestamp. This sequence is the historical integration sequence. Once we extract the historical integration sequences, we calculate the integration process efficiency for each of them. To do so, we calculate the cumulative cost and gain of each integration step, where the cost is the number of per web conflicts to solve and the gain is the number of integrating pull requests. Let's see an example of an historical integration sequences of the Anteler4 project. Here is the pull request integration sequence, and this is the related per web conflict graph. Let's start by considering that the first 10 pull requests of the integration sequence do not conflict with each other, so they are integrated at zero cost, since the project administrator does not have to solve any conflict to integrate them. Since pull request 1996 conflicts with 7 already integrated pull requests, it is required to solve conflict with those pull requests to integrate it. Therefore, the cost of integrating pull request 1996 is 7. And as the pull request 1983 and 1955 do not conflict with any already integrated pull request, then they are integrated at zero cost and the cumulative cost is still 7. Pull request 1974 conflict with pull request 2011, so the cumulative cost is 8. The following 12 pull requests do not conflict with the previously integrated pull requests, thus they are integrated at zero cost and the cumulative cost is still 8. Pull request 1990 conflict with 12 already integrated pull requests, so the cumulative cost is 20. And pull request 2083 do not conflict with any other pull request, already integrated pull request, so the cumulative cost is still 20. And finally, the pull request 1930 conflict with pull request 1951 and pull request 2083. Thus, the integration cost is 2 and the cumulative cost is 22. Next, we map the cumulative cost gain table to a trajectory where x is the cumulative cost and x is y is the cumulative gain. Each coordinate is an integration step, and the line between points is the integration step cost. The trajectory models the integration sequence, and the area under the trajectory represent the integration process efficiency, because a larger area means that a higher gain is achieved at a lower cost. The integration process efficiency corresponding to the historical integration sequence is 449. In addition, the number of conflict resolutions is 4, corresponding to the integration of pull requests 1996, 1974, 1990, and 1930. Next, we apply our approach to the set of pull requests corresponding to the historical integration sequence to then calculate the integration process efficiency of the pull request group integration sequence obtained by our approach. Following with the example of the previous slide, we obtain the per web conflict graph for the set of pull requests of the historical integration sequence. Then we obtain the corresponding color graph by applying the second step of the approach. Next, we obtain the pull request group graph corresponding to the color per config graph. And lastly, applying the fourth step of our approach to the pull request group graph, resulting in the following pull request integration group integration sequence. We evaluate the integration sequence optimized by our proposal by calculating its integration process efficiency in the same way that we calculate the historical integration process efficiency. The 25 pull requests corresponding to C0 can be automatically integrated. The 3 pull requests corresponding to C1 do not conflict with each other, but 14 per web conflict need to be solved to integrate them into the target branch. And finally, it is needed to solve 8 per web conflict to integrate the pull request belonging to C2. The figure shows both the historical and our optimized integration trajectories. The integration process efficiency corresponding to our optimized integration sequence is 578, 28.73% higher than the historical one. And in addition, its number of conflict resolution is 2, corresponding to the integration of C1 and C2. I'm going to present the result obtained in our work. We apply our proposal to 7 representative historical integration sequences of the Antel 4 project. The selection criterion for these sequences is the number of unconflicting pull request groups obtained by applying the coloring algorithm to the per web conflict graph corresponding to the integration sequences. This table shows information about the per web conflict graph corresponding to the selected integration sequences, the number of per web conflict, the number of pull requests and the number of per web conflict correspond to the number of nodes and edges of the per web conflict graph, respectively. The number of potential conflict resolution correspond to the worst case of the number of conflict resolution for the case study. And finally, the number of unconflicting pull request groups correspond to the number of groups that we obtain by applying the coloring algorithm to the per web conflict graph of the case study. This table shows the comparison between the historical integration efficiency and the optimized integration process efficiency obtained by our proposal for each case study. We observe that for all case study, our approach improves the historical integration process efficiency. The integration process efficiency improvement percentage is between 28.73 and 156.52. In addition, the number of conflict resolution resulting in the proposed pull request group integration sequence is less than or equal to the historical one. So as a conclusion, in this work, we optimize the efficiency of the integration process through pull request prioritization. Our approach is able to automatically calculate a sequence of unconflicting pull request groups that minimize the number of conflict resolution and orders the integration of the groups according to the integration process efficiency. The result of our study shows that the integration process efficiency of the integration sequence calculated by our approach is higher than the historical integration process efficiency from 28.73% to 156.52%. And as a future work, we plan to conduct an empirical study on a large number of projects that use pull requests intensively. We also plan to propose a tool integrated into platform that support pull-based development, such as GitHub, Bitbucket, etc., in order to further evaluate the usefulness of our proposal, study the side effects on the work habits when using our proposal, and discover additional factors that can be used to improve the integration process efficiency performed by our proposal. We also plan to study accurate model for the evaluation of the cost and gain of pull request merges. If you have any question, I will be happy to answer them.